Identities, inverses, and determinants. So an identity matrix is a square matrix with all entries 0 except for a diagonal of 1s. So for a 2 by 2 matrix, that looks like this, 1 0 0 1. For a 3 by 3 matrix, similar, and you can imagine the pattern 4 by 4, 5 by 5, etc. So identity matrices can be thought of as the matrix equivalent of the number 1, and on its own this is a pretty irrelevant sort of fact, but this is an important tool in enabling us to come up with the inverse matrix, and the inverse matrix is imperative in matrix arithmetic since we don't have division as an operation with matrices. So just to skip ahead a little bit, say for example, if we're solving the equation 2x equals 5. We know that to solve equations we do the inverse operation to both sides of the equation in order to isolate x on its own. So in this case, the inverse operation to multiplying by 2 is to divide by 2. So we get x equals 5 on 2, or 2.5. Now if we're dealing with a matrix equation, where A, X and B are all matrices, we can't divide. So what we need instead is another way to eliminate this A from here, to undo multiplying by A. And that's where the inverse of matrix A comes in. And that's the same kind of idea as if we go back to the original equation of 2x equals 5. Instead of dividing both sides by 2, we could think about that instead as multiplying both sides by 1/2, and think about 1/2 as being sort of like the inverse of 2. It's not quite an inverse, but they're inverses because when we multiply them together they produce 1, which is what we want to be able to do. So this idea of what is the matrix equivalent of 1 is important in us establishing an inverse matrix, which allows us to solve equations involving matrices. So on its own it's fairly trivial. So one of the key properties of an identity matrix is that any matrix multiplied by the identity will just equal itself. That's where it's like 1. And also matrix multiplication with the identity matrix is commutative. So A times I is the same as I times A, and they both just equal A. Let's just have a quick check of that while we're here. So if we imagine 1, 2, 3, 4 as our matrix A, and if we multiply that by the 2 by 2 identity matrix, so rows times columns, so 1 times 1 plus 2 times 0, 1 times 0 plus 2 times 1, bottom row times left column, 3 times 1 plus 4 times 0, bottom row times right column, 3 times 0 plus 4 times 1. And we find that A times I does indeed equal A. Let's just check if we did it the other way. 1 0 0 1, 1 2 3 4. So this time I times A. Top row times left column, 1 times 1 plus 0 times 3. Top row times right column, 1 times 2 plus 0 times 4. Bottom row times left column, 0 times 1 plus 1 times 3. And bottom row times right column, 0 times 2 plus 1 times 4. And again, we find that I times A equals A. So the identity matrix we're going to need as part of the next process. So as I said, an inverse matrix is what we're aiming for. So given a 2 by 2 matrix A, there is another matrix, which for now we'll call B, so that A times B is the same as B times A, and that they both multiply together to give the identity matrix. And if that is the case, we would say that B is the inverse of A. It essentially undoes A. We can think about that, as it says in this third sentence down here, similar to the half being the inverse, if you like, of 2, because half times 2 is the same as 2 times a half, which equals 1, and they cancel each other out. So it's a useful tool in trying to solve an equation. So as I said, if this is the case, if this property is the case, if the multiplication is commutative, and if both multiplications give the identity matrix, then we say that that matrix is the inverse of A, which we denote A to the negative 1. And we've seen that notation before: inverse trig functions, inverse functions, etc. Okay, so this is the key property of the inverse matrix. So let's get on to trying to see if we can establish how to work out the inverse matrix. So we're going to do this the long way. If a question says find the inverse of A, you wouldn't do this, but what we want to do here is try to use the property that where we know that A times the inverse of A equals the identity matrix. We want to use that property to try and work out what is the identity matrix and see if we can come up with a formula. So what we've got to understand here is we know what A is and we know what I is, so surely we've got enough information here to solve for the inverse. Okay, so let's set that up. So A is 1, 5, negative 2, 3. The inverse matrix is unknown. I'm going to call that W, X, Y, Z. And our identity matrix we know 1, 0, 0, 1. So we're trying to find what does this matrix have to be in order that when I multiply A by it, it gives me the identity matrix. Okay, so there's a bit of algebra here, but it's algebra we're capable of. So as I said, this is not a process you're going to need to do, but I want you to follow it and understand what's happening and start to see the patterns and see where these formulas are coming from. Okay, so let's expand out this matrix multiplication. So rows times columns, top row times left column, so it's going to give us 1w plus 5y. Top row times right column gives us 1x plus 5z. Bottom row times left column, minus 2w plus 3y. Bottom row times right column, minus 2x plus 3z. And we know that that equals 1, 0, 0, 1. Now we have a 2 by 2 matrix equal to another 2 by 2 matrix, and so we can equate elements of those two matrices. So we can say that w plus 5y is equal to 1, and minus 2w plus 3y is equal to 0. So we have a pair of simultaneous equations in w and y. So I'm going to take the top equation and multiply it by 2 to get 2w plus 10y equals 2. And then I'm going to add those two equations to eliminate w. So that's going to give me 13y equals 2, so y equals 2 on 13. We can go back to, I'm going to go to the first equation, which tells me that w equals 1 minus 5y. So that is 1 minus 5 times 2 thirteenths, which is 10 thirteenths. And 1 minus 10 thirteenths is 13 thirteenths minus 10 thirteenths, so 3 thirteenths. So we have y and we have w. Okay, now let's get the pair of equations in x and z. So I'm just going to go up the top here, give myself some space. So we're going to have x plus 5z is equal to 0, and minus 2x plus 3z is equal to 1. So the equations are very similar apart from having different letters, but also the right hand side is different, the numbers around the other way. So that's going to generate different answers. So again though, process is going to be the same because they're the same coefficients. So we're going to multiply the first equation by 2 to give us 2x plus 10z equals 0. And then we're going to add the two equations to eliminate x. So again, 13z this time equals 1. So z equals 1. We know that x in this case is negative 5z, so that's just rearranging the first equation. So that's negative, it's 1/13 with z. So x is negative 5 times z, so that's negative 5/13. So we've got z and we've got x, so we've got our four things. So we know that a was 1, 5, negative 2, 3, and we can see that the inverse of a is wxyz, so 3 thirteenths, negative 5 thirteenths, 2 thirteenths, and 1 13th. Now we have that common denominator of 13, so if we want we could take that out. So we get 1 on 13, 3, negative 5, 2, 1. So we can see that the numbers are very similar from our original matrix to our inverse matrix. What's happened is these two numbers on the downward sloping diagonal have been switched around, and the other two numbers on the upward sloping diagonal have remained in the same position, but they've been multiplied by negative 1. So those are key points in how we calculate the inverse matrix. The other thing though is that the whole thing is divided by 13, and what's not immediately apparent from what we've done here is where does that 13 come from? How do we calculate that 13 without having to go through this lengthy process? So what I'm going to do is, instead of looking at this case with a numerical matrix, let's really generalize this out now. Let's have a look at finding the inverse of A, B, C, D using the same process. So we know that A times the inverse of A has to equal I. So we've set up this equation here. So this is A. This is going to be our inverse of A. That's what we're going to be trying to solve for. W, X, Y, and Z, just like we did in the previous example. And this is I. So same as before, let's expand out the left-hand side here. So rows times columns, so top row times left column gives us AW plus BY. So obviously we're going to be dealing with a lot more letters here, but the process is exactly the same as what we did with the numbers. So again, you don't need to replicate this. We're trying to come up with a formula. I want you to follow it, okay? See if you can follow the algebra. See if you can see what's happening. Have some understanding of where that random formula comes from so we can then go ahead and use it. So top row times right column, AX plus BZ. Bottom row times left column, CW plus DY. Bottom row times right column, CX plus DZ. And that is equal to 1001. So again, we can equate elements to form simultaneous equations here. So let's deal with the W's and Y's. So we've got AW plus BY equals 1, and CW plus DY equals 0. So we're going to need a common term so we can eliminate. So I'm going to multiply the top equation by C and the bottom equation by A. So we're going to get ACW plus BCY equals C. And we're going to get ACW plus ADY equals 0. We're going to subtract them to eliminate the ACWs. So we're just going to have BCY minus ADY equals C. I'm going to factor out the Y. BC minus AD equals C. And so Y is C over BC minus AD. Now we're going to need to substitute that back in to find W. So I'm going to go into the second equation, which has a 0, because the second equation, if I rearrange it, tells me that CW equals negative DY. So negative D times Y, which we've got down here, so that's going to be negative DC over BC minus AD. And then I'm going to divide both sides by C, which is fairly simple because there's a C on both sides. So W is just going to be negative D over BC minus AD. Now, because I've got a negative on the numerator and I've got a subtraction on the bottom, I'm going to multiply both top and bottom of this fraction by negative 1. So we get positive D and AD minus BC. Okay, so we've got W and we've got Y. And now we need to solve the other pair of simultaneous equations to find X and Z. Okay, so I've just moved us on to a new page. So this is the pair of simultaneous equations in X and Z over here on the left that we'll need to solve. I've also just copied the results of what we found from the other pair of simultaneous equations. So we've found Y and we've found W. Okay, so let's solve this pair of simultaneous equations. Again, the process is going to be very similar. So we're going to multiply the top one by C, multiply the bottom one by A. So we're going to get ACX plus BCZ equals 0. And ACX plus ADZ equals A. And we're going to subtract. So we get BCZ minus ADZ equals negative A. Factor out the Z. BC minus AD equals negative A. So dividing by the bracket, so negative A over BC minus AD. And again, I'm going to multiply top and bottom by negative 1. So I've got A over AD minus BC. Alright, so now we've found Z. Let's add that up over here. And then we just need X. So I'm going to substitute back into the first equation because the first equation tells me that AX equals negative bz. So that is negative AB over AD minus BC. So I've just substituted Z in here. Dividing both sides by A, we've got A on both sides, so X is just negative B over AD minus BC. Now I'm going to leave that negative in the numerator. I'm going to add this up over here because it's helpful if they all have the same denominator. So we've got all three of the 4 over AD minus BC. Y is over the negative of that, so I'm actually going to multiply the top and the bottom here by negative 1 and go back to negative C over AD minus BC. So now we've got all 4 over the same thing. Okay, so let's have a look at what we started with. So here's our results. So we know that A was A, B, C, D. And the inverse of A was W, X, Y, Z. And we've now worked those things out. So W is negative, oh no, sorry, that's Y. W is D over AD minus BC. X is negative B over AD minus BC. Y is negative C over AD minus BC, and Z is A over AD minus BC. So we've got that common factor of 1 over AD minus BC, and if we take that out, we've got D, negative B, negative C, A. Okay, so we're seeing those same patterns that we saw in the numerical example. We swap these two around and we make these two negative. But now we're able to see where that 13 came from in our previous example. It's AD minus BC. Okay, so we've established our rule for the inverse. So 1 over AD minus BC, and then swap the downward sloping diagonal and make the upward sloping diagonal negative, or multiply by negative 1. So this number here, AD minus BC, we refer to that as the determinant. We denote that with just det of A or B or whatever our matrix is called. And the determinant, so the determinant is just the AD minus BC. Students commonly mistake the determinant as being 1 over AD minus BC. So the determinant is just the AD minus BC. To find the inverse, we do 1 over the determinant and then multiply by the matrix. So obviously we're dividing by this determinant, AD minus BC. So that means there's going to be some restrictions here. So the inverse requires us to be able to divide by AD minus BC, which means that the inverse will only exist if AD minus BC, which is the determinant, if that does not equal 0. So if that determinant doesn't equal 0, the inverse will exist, and we say that the original matrix is a regular matrix. It has an inverse, it's a regular matrix. If it doesn't have an inverse, that is if the determinant is 0, we call that a singular matrix. Okay, let's have a quick look at some examples. So find the determinant and the inverse of A. So determinant we know is AD minus BC. So that is going to be 1 times 2 minus negative 2 times negative 5, which is 2 minus 10, which is negative 8. We then need the inverse, which we know is 1 over the determinant. And we swap these two around and we make these two negative. So we're going to have 1 over negative 8. We're going to swap those two around and we're going to multiply these two by negative 1, which will make them both positive in this case. So that is our inverse matrix. You can expand it out if you want. There is no need to, but if you do, make sure that you simplify your fractions. So negative 1/4 rather than negative 2/8. Both are perfectly valid. Generally, we wouldn't bother to expand it out. Okay, last example, a slightly different way of testing your understanding of the same knowledge. So we've got this matrix with an unknown number in it, k, and we wish to find that unknown number k given that we know that A is a singular matrix. So a singular matrix means that it has no inverse, which means that the determinant must be equal to 0. So we want to have a look at the determinant of this matrix A. We know that is AD minus BC. So negative 3 times 1 minus 4 times k. And that has to equal 0. So we've got negative 3 minus 4k equals 0. So 4k equals negative 3. So k has to equal negative 3/4 if this is to be a singular matrix. So go and practice finding some determinants and inverses. You don't need to go through that lengthy process. We've got a formula now. Use it, learn it, know how to use it. Good luck.